Today we are going to continue with electric multipoles. In this case, we want to study a little bit further the concepts of the monopole moment and the dipole moment. On previous videos, we saw that, well, we can find a definition for the electric potential measured on a point P, which is located with a vector r with coordinates x, y, z. Okay, so in this case, well, we found that, for example, the monopole term is defined in this way, and the dipole term is defined in this way. These are both cases that we are going to study in this video. Okay, so before getting into those concepts, I want to introduce, well, a very famous concept which is known as direction cosines that we are going to use actually in the dipole term. Okay, so in this case, looking at, for example, well, we have a vector r here that is pointing to P, and we have this vector ri which is pointing to the charge qi. Well, we know that, for example, r dot ri, well, it will be the magnitude of r times the magnitude of ri times cosine of theta I. Okay, so we can say that cosine of theta I is equal to r dot ri, and this is divided by, let me just write this as rri. Okay, but well, it's easy to notice that this expression that I have here can be seen as a unit vector r dot ri over ri. Okay, so I need to watch carefully this vector that we have here, because we can define it on another way, and here is where we are going to introduce the direction cosines. We can see that, well, let me draw it again. If we have the reference system here, let me write this vector r. Okay, so we are interested in finding the angles that are between this vector and the axis. For example, the x-axis here. Well, we are going to get an angle alpha here, okay, for this vector with the axis. Okay, so we know that the angle between two vectors can be found with actually this formula that we have here with the dot product rule. So in this case, we can, for example, let's introduce a vector that is going to be x in the x direction, okay, or just x, a unit vector x, to be easier. So we can say that the angle between x and r can be found with this formula. We have that x dot r is going to be, well, the magnitude of x, but it is 1 because it is a unit vector, times the magnitude of r, and then cosine of alpha. Okay, so we can say that cosine of alpha is going to be equal to x dot r over r. Okay, perfect. But we know that in our case, r is defined as x, y, z, and, well, the vector x is just going to be, well, 1 times x. So if we make the dot product between these two vectors, well, we are going to get that x dot r is going to be equal to x. So we get that cosine of alpha is going to be x over r. Okay, perfect. But let me point out that it's easy to notice that r, a unit vector r, is going to be defined as x, y, z all over r. Okay, so it is a vector divided by its magnitude. Okay, so the x component is actually x over r, and that is what we found here. Okay, so that means that, well, this vector r, the unit vector r, is going to be defined as cosine of alpha for the x component, and let's say that if this is y and this is z, and we name this angle as beta and this angle as gamma, well, we can say that the components of r is going to be cosine of beta and cosine of gamma. Perfect, but just to make it simpler, we are going to define the direction cosine of alpha as Lx, then cosine of beta as Ly, and then cosine of gamma Lz. Okay, the direction cosines for r. Okay, so this is the unit vector r. Okay, so if we take this concept and we introduce it here, well, we are going to get that, well, we are going to have here Lx, Ly, Lz dot, well, Ri, but Ri, well, it can be seen as a vector that has coordinates xi, yi, zi. Okay, so the components of Ri are those. So we get xi, yi, zi, and then all over Ri. So let me write this here. We are going to get that cosine of theta I is equal to, well, Lx times xi plus Ly yi plus Lz zi all over Ri. Okay? Perfect. So for now we are going to leave this in this step. So we are going to check what happens with this term that we have here, the monopole term. Okay, so we know that phi m of r is going to be, well, the sum from I equals 1 up to n of qi over 4 pi epsilon 0 r. We see that for this sum, all this that we have here is constant, so we can take it out, and we are going to get 1 over 4 pi epsilon 0 r. So we need to notice that we have a sum of something here, okay? In the context of electric multipoles, these sums that are going to be of many terms, in this case it's just one, but on other tries we are going to get that these sums are going to be applied to some other terms. Well, these sums are going to define what we know as electric moments. Okay, in this case, this sum Qi is going to define the monopole moment. Okay, because it is for the monopolar term of the electric potential. So this is the monopole moment. And well, looking that we have a discrete distribution of electric charges, it is easy to notice that the sum of these Qi's, Q1 plus Q2 plus Q3 all the way up to Qn, well, it's just going to be the total charge of the system, and we are going to name that charge as Q. Okay, so we can say then that the monopole term of R, well, it's just going to be Q over 4 pi epsilon 0 R. Okay, which is very similar to the electric potential generated just by one charge. Okay, so if we have a charge Q and we want to measure the electric potential on a point P, well, it is very easy to calculate that. We just need the distance that separates the point P from the charge, and well, we use this formula here. Okay, so the monopole term is equivalent to a system that only has one charge, and that charge has a value of Q, where Q is the sum of every charge. Perfect. Okay, so there is no too much to say anymore about this, just that, well, the monopole moment is just defined as Q, the net charge of the system. Okay, perfect. So let's go to the dipole term of the electric potential, which is a lot more interesting than the monopole term. Okay. Okay, perfect. So I rewrote the term here, and as I said, The interesting term is going to be the one that is inside the sum. So first of all, looking that this is a constant, we are going to take it out. Okay, so this is going to be 1 over 4 pi epsilon 0 r squared times the sum from I equals 1 up to n of qi ri cosine of theta I. So looking that this is inside the sum, it is going to be known as, well, the dipole moment. Okay, the sum that we have here is going to be the dipole moment. Okay, but what happens with that sum? Okay, well, first of all, remember that what we have calculated here, it seems very similar to the dipole moment because we have here an Ri cosine of theta I. And here, if we take this Ri to the other side, we are going to get the same. So let me write that. So we have that Ri cosine of theta I is equal to all these that we have here. So we are going to take this expression and to plug it into this. So we get that the dipole term of the electric potential is going to be equal to 1 over 4 pi epsilon 0 r squared times the sum from I equals 1 up to n of qi times Lx xi plus Ly yi plus Lz zi. Okay, and it's very easy to work with this expression. We are going to get that this is 1 over 4 pi epsilon 0 r squared times, well, this is going to multiply, well, Lx times the sum from I equals 1 up to n of qi xi. Okay, I'm taking out the Lx because it does not have any I index. So it's just a constant that we can take out from the sum. And this is going to be plus Ly, the sum from I equals 1 up to n of qi yi, and then plus Lz times the sum from I equals 1 up to n of, well, qi zi. Okay, perfect. So remember that we mentioned that Lx, Ly, Lz are the components of the unit vector r. Okay, so we have that components here, here, and here. So if you see, it's kind of similar to a dot product between two vectors. Okay, I think it's not very hard to see. So we are going to express this as a dot product of two vectors. But what vectors are we going to introduce? Well, we can see this as the next 1 over 4 pi epsilon 0 r squared times Lx, Ly, Lz dot the next, the sum from I equals 1 up to n of qi xi, the sum from I equals 1 up to n of qi yi, and then the sum from I equals 1 up to n of qi zi. Okay, and this sum, well, this vector of sums that we have here, it can be seen as the sum from I equals 1 up to n of qi times a vector which is going to be xi, yi, zi. So it is a vector, and this sum is going to multiply every component of that vector. Okay, and this vector, well, is just ri. Okay, so that means that we can see the dipole term of the electric potential as 1 over 4 pi epsilon 0 r squared. And then, well, we saw that this is the unit vector r. So this is going to be r dot, and then the sum from I equals 1 up to n of qi ri. Okay, perfect. Okay, so this is the interesting term that we have in this equation, because this is what we are going to define as the dipole moment, and we are going to name it P. So that means that the dipole term for the electric potential is going to be defined as 1 over 4 pi epsilon 0 r squared times r unit vector r dot P, which is the dipole moment. Okay, so this will be another way to express the dipole term on the expansion for the electric potential in terms of the electric multipoles. Okay, and well, looking at this is a unit vector, we know that it is the vector r divided by its magnitude. Okay, so we can rewrite this as r dot p over 4 pi epsilon 0 r to the third power. Okay, perfect. So that will be like the most important result of the video. Other thing to mention that is very important is that, well, in this case we have a discrete distribution of charges. What happens if we have a continuous distribution of charges, where, for example, the charge density, well, it can be defined, for example, on a volume, rho equals well, the charge divided by the volume. Okay, well, in these cases we know that to calculate the total charge on a continuous distribution of charge, well, we need to take the integral of the density of charge times a volume differential, and we are going to integrate on that volume. Okay, so in this case, well, we need to mention that the monopole moment will be defined in this way, and this is for continuous distribution. Okay, so yeah, it was important to mention this. And what happens in the case of the dipole moment? Well, we saw that in this case we had a sum from I equals 1 up to n of qi ri. We need to change that sum for an integral, because in this case we do not have discrete charges on the space. We have a continuous distribution. So how can we replace that sum? So that sum, well, it will be equivalent to the next. The dipole moment is going to be defined as the integral of, well, the charge density, the volume charge density, okay, times, well, the vector r that is pointing, remember that this vector is pointing to the, in this case, to the charge distribution, okay, the charge distribution that generates the electric potential, okay, that is important. And this, well, is just the density of charge distribution. And we are going to integrate on a volume, okay. Okay, so the difference is that, well, we are including a vector r here, okay, and well, that is the expression for the dipole moment on a continuous distribution. Notice that, looking that we have a vector here, of course the dipole moment is also going to be a vector, so we need to integrate this to get the dipole moment. Okay, perfect. So this will be a good time to finish the video, and if you have any question, just leave it on the comments.